Welcome back. We are going to describe the reason why objects move or change state of motion using Newton's laws. These are going to be our learning goals. We are going to explain what is meant by the term inertia and relate it to mass, and then state Newton's laws of motion and describe their implication. We will also try to apply Newton's laws to explain acceleration. It will be the center of this lecture indeed. Now, let's recap what we've done so far and see where we are going. We've described motion. We now have some terms for describing motions. So, we've been able to describe the body's position, and we also came to appreciate that if a body changes position from one point to another one, we say it has moved, and if it has moved, it must have a speed. That is, how much distance has it traveled in a unit time. We've also learned that the speed can also change with time, and that results in acceleration. So the question is, what causes acceleration? In other words, what causes an object to change its state of motion or rest? Remember, acceleration can come in various forms. Indeed, if a body starts moving from rest, it has accelerated. And if it stops from moving, it has decelerated. They all constitute acceleration. Then if it changes speed or velocity, it has accelerated. And changing direction also constitutes acceleration. So still on our question, what causes acceleration? In other words, what causes change in velocity? We will understand this better when we start talking about Newton's law. The three laws do explain why objects do accelerate. In other words, why they change their state of rest or motion. The first law, also known as the law of inertia, states that a body remains in its state of rest or constant speed unless a resultant force acts on it. So a state of rest or constant speed unless an external force or resultant force acts on it. Now, there are several implications to this law. What it means is that every object at rest will want to remain at rest. Every object prefers being, if it's at rest, it prefers to be at rest. If you try to move it, it will initially resist. At the same time, it tells us that if a body is moving with a constant velocity, then it will want to continue moving at that constant velocity. If you try to stop it or move it further, it will try to resist. That's what the first law is telling us. It also tells us that objects initially resist attempt to change their state of motion. Yes, I've said that already. And the amount of resistance, that's what we call the inertia, and it depends on the mass. Inertia. So the greater the mass, the greater the initial resistance to any attempt to move it. So if we have a very heavy duty vehicle, it is very, very difficult to give it a push. But if you have a toy car which is designed just as the heavy duty vehicle, you can give it a small push and it will start accelerating. You see. So the reason is that the heavy duty vehicle resists the force much better than the toy car. That's it. So the inertia, the amount of resistance, depends on the mass. That's what we are saying. Now take note of this. Before any object can change their state of rest or motion, force must be applied to it before they can change their state of motion. In other words, before they can accelerate, force must be applied. We move on to the second law. That law states that the acceleration is directly proportional to the force applied to it. So if we give a force to an object, or we apply a force on an object, that object will accelerate. It it answers the earlier on question. So the force accelerates a body. So the acceleration of the body depends on how much force it has been given. So if you give it greater force, it will accelerate faster. That is it. Now, let me take you through some of the implications of this law. First of all, inertia, which is invariably the same as the mass. In physics, mass is a measure of the amount of initial resistance to applied force. Take note of this. When you go to chemistry, they will tell you mass is the amount of substance in a body. But it doesn't explain so many things in physics. So we better use the term inertia to represent mass. So we say mass is a measure of the amount of initial resistance to force. So we can substitute the word mass with the term inertia. So the greater the mass, the greater the ability to resist an external force applied to the body. So from this we know every object will try to resist. From the first law, every object will try to resist any applied force that tends to change its state of motion. In other words, any force that tries to accelerate, the object will resist. So the force overcomes the resistance and causes the body to change state of motion or rest. So this force that is applied to the body will overcome the mass and then cause it to accelerate. So the force that will be applied to it is the product of the mass, the initial resistance, or the inertia multiplied by the acceleration. So if we apply a certain force to the body, and the body is very, very huge, has a very big mass, then the acceleration will be very small. If the mass is very, very small, then acceleration will be very, very high. So the force determines how much a body will accelerate. Okay, let's take this simple example. We've seen this graph before, and we are going to apply Newton's laws to it and do some calculations. We are expected to use the graph here. It represents the motion of a body of 15 kilograms. So we are supposed to determine the forces at various sections of the speed time graph. Now, for the first 10 seconds, if we want to find the force, then according to Newton's second law, we need the mass and then the acceleration. The mass has been given us as 15 kilograms. Now, how do we calculate the acceleration? The acceleration is simply the change in velocity between 0 seconds and 10 seconds. The body changed speed from 0 to 20. So the initial speed is 0 and the final speed is 20. Now the time change, it took 10 seconds from 0 to 10. So the final time was 10 minus the initial time, which was 0. So it took 10 seconds for this change to occur. So change in velocity over change in time gives us 2 meters per second squared. Sorry, we should have a square here. 2 meters per second squared. Okay, so the force can be calculated now. We have the mass, which is 15, multiplied by the acceleration, which is 2 from here, and we get 30 Newton. So we can move on to the second question. That one is asking us to find the force applied to the body between the 10th and the 15th seconds. Again, we start thinking about the final velocity and the initial velocity and then the time change. On the graph, we are talking about this range of the curve between 10 and the 15. Now, the final velocity was on the 15th second, and that was 10 meters per second. That's what we've written here. So the final velocity was 10 meters per second. What was the initial velocity? The initial velocity was on the 10th second. We are starting from 10 to 15. So initial, then final. So the initial was on the 10th second. Remember, this axis is the time axis. 10th second. And it was running at 20 meters per second. So we subtract 20 from 10 divided by 10 minus 15. And if you calculate this, you are going to get negative 2 meters per second squared. Now, why negative? The negative tells us that it is decelerating, it is decreasing in speed. And if it is decreasing in speed, then the force is opposing motion. It is an opposing force. And a force pushed it so fast from, moved it so fast from here all the way here. And to reduce speed, we must apply force in the opposite direction. That's indicated by the negative. The force that will decrease the speed will be negative 30 newtons. The third question was asking us to find the acceleration during this period. The final velocity was 10, the initial velocity was 10, and the velocity change was 0. There was no change in velocity, and as we have always been talking about, there's no change in velocity, and so there's nothing like acceleration. Up here, we have 10 minus 10, which is 0. So we don't care how much time it took. The acceleration will be 0. If acceleration is 0, then there is no force acting on the body. Okay, so the last one applies to, concerns this part of the journey. I will leave that one to you to try it yourself. Move on to the third law. It's often stated so simply, by the understanding and application is it's quite difficult for many people. Now, it's very common to hear that action and reaction are opposite and equal. In other books, they will write, to every applied force there is an equal but opposite force. To every applied force there is an equal and opposite force. These are some of the implications. That forces come in pair. Forces always come in pairs. They are opposites, but they are equal. They are equal in magnitude. So every force that you apply, there is an equal one in opposites. We can also rewrite it in a simple way. When two bodies A and B interact, A exerts a force on B and B exerts equal but opposite force on A. In effect, what we are saying is that the effect of the action force may be different from the effect of the reaction force. So these are the consequences of the third law. All right. So I have these online resources for you. I want you to watch them and you understand these laws that I've given you much better. You can have some exercises that I'll give you for you to try, and you can also ask more questions on the WhatsApp platform. Thank you.